is a very special and indeed a unique pleasure to be able to introduce to you the very first plenary speaker of this edition of the International Congress of Mathematical Physics. The speaker is a brand new recipient of the Henri Poincaré Prize, Professor Yoshiko Ogata of Tokyo University. Professor Ogata is well known for her work in quantum statistical mechanics, both in and out of equilibrium, as we heard in the extensive laudatio by Hal Tasaki. As for me, let me just recall a few things, or rather repeat in this case. So for instance, her work on non-equilibrium statistical physics and in particular construction of non-equilibrium states and the foundation, the algebraic foundation of linear response theory. And more on the side of equilibrium statistical mechanics, the achievement of Lieb-Schultz-Matisse type theorems for models in absence of continuous symmetry breaking. And as a last item, her work on the classification of topological phases of ground states of quantum spin systems. Now, the pleasure of introducing her would have been even more complete if I could have handed her in person the medal for plenary speakers of this Congress. It is not possible given the circumstances, and it will be delivered. I also have one small announcement, and that questions should be asked at the end of the talk. And now, without any further ado, let me ask Professor Ogata to give her talk by the title, Classification of Symmetry-Protected Topological Phases in Quantum Spin Systems.
Thank you very much, Michele, for kind introduction. Do you hear me? I hope. Okay, so let me start my talk. So thank you very much for giving me, I would like to thank the organizing committee for giving me this opportunity to talk here today. It is a greatest honor for me. And I'm going to talk about classification of symmetry-protected topological phases in quantum spin system. So let me start. So symmetry-protected topological phases are phases of Hamiltonians satisfying the following three conditions. First, this Hamiltonian has a unique gapped ground state. Namely, ground state is unique and there is a gap between the lowest eigenvalue and the rest of the spectrum. Second, this Hamiltonian satisfies some fixed symmetry, let's say G here. Third, this Hamiltonian can be smoothly deformed into a trivial on-site Hamiltonian without closing the gap. So there is a smooth path of gapped Hamiltonian connecting our Hamiltonian and on-site trivial Hamiltonian. So we are interested in the set of all Hamiltonians satisfying these three conditions. And we would like to classify them. We would like to classify them with respect to the following criterion, that is, we say two Hamiltonians are G equivalent if they can be smoothly deformed into each other via a path of gapped Hamiltonian without breaking the symmetry. So note that because of this third condition, any Hamiltonian in this set can be deformed into each other without closing the gap. However, now we are requiring some additional condition, that is without breaking the symmetry. So we are requiring the symmetry to be preserved along the path. Because of this additional condition, this set may split into possibly multiple equivalence classes with respect to this classification. And the resulting equivalence classes are the symmetry-protected topological phases in the title. And this is a classification problem of symmetry-protected topological phases, so-called SPT phases. Now, about this SPT classification problem of SPT phases, physicists and algebraic topologists say the following. They say SPT phases should be understood in terms of invertible quantum field theory. And because of that, they say for a finite group, it should be classified by a Pontryagin dual of Bodism group on classifying space of G. So they say this SPT phase should be classified by a Pontryagin dual of Bodism group on classifying space, which looks a bit complicated thing to analyze, at least for me. But in low-dimensional system, this thing becomes much simpler object. Namely, in 1 and 2-dimensional system, they become second and third group cohomology. In any case, I think it will be great if we can derive such a Pontryagin dual of Bodism group on classifying space predicted by invertible quantum field theory out of general microscopic model. I think that would be great if we can derive such thing out of general microscopic models. And this talk is about research in this direction. Namely, we will derive second and third group cohomology invariant out of 1 and 2-dimensional quantum spin system. That is what this talk is about. Now, so let me try to speak a little bit more precisely now. In this talk, we consider this SPT classification problem in operator algebraic framework of quantum spin system. The advantage of this operator algebraic framework is that we can treat the infinite system directly. And the reason why we would like to treat infinite system is because our invariants get trivial in finite system. The situation is pretty much similar to, pretty much analogous to what happened to Fredholm index. Recall that Fredholm on finite dimensional Hilbert space, Fredholm index of any operator is 0. But if you go to infinite dimensional Hilbert space, then you will find some Fredholm operator with non-trivial Fredholm index. And a pretty much analogous thing happened to our SPT business. And for this reason, I think this operator algebraic framework is the most natural framework to consider this classification problem of SPT phases. So now I'd like to introduce you this operator algebraic framework. In this operator algebraic framework, is a quantum spin system defined as follows. So throughout this talk, I fix some natural number D, and nu will indicate spatial dimension, which will be 1 or 2 for us. And nu dimensional quantum spin system is defined as an infinite tensor product of D by D matrices along nu dimensional lattice. So this is the definition of nu dimensional quantum spin system. And for each subset of nu dimensional system, nu dimensional lattice, we can do the same thing. Namely, we can consider the tensor product of D by D matrices along this gamma and obtain some sister algebra A gamma, which can be naturally regarded as a subalgebra of nu dimensional quantum spin system. And with this natural identification, we say that element in A gamma has a support in gamma, or we say element in A gamma is localized in gamma. So this is a quantum spin system in operator algebraic framework. I also would like to specify what I mean by a state in this talk. A state on a sister algebra is a positive in this sense, and unitary in this sense, linear functional on the sister algebra. And this corresponds to the procedure of taking expectation value of each observable in our physical state. So that is state in this talk. Now, in this operator algebraic framework of quantum statistical mechanics, physical models are given by interactions. So let me define interaction. An interaction is a map phi from the set of all finite subset of new dimensional lattice to our quantum spin system, satisfying this condition. So for each finite subset X, we assign some element phi X of our new dimensional quantum spin system, and it is supposed to represent the interaction term between spins inside of this X. As a result, it should be self-adjoint and it should be localized in X. So this is interaction. And out of interaction, we would like to construct dynamics. In order to do so, we need to, this interaction needs to satisfy some kind of a nice locality condition. And there can be many ways to introduce such a nice kind of condition, nice locality condition, but the easiest of that kind is uniformly bounded and finite range. So let me introduce this easiest one here. Interaction phi is of finite range if there exists natural number satisfying this condition. Namely, if X has a diameter larger than M, then corresponding interaction term is 0. And uniformly boundedness is literally uniformly boundedness, like this. Now, from interaction, we would like to construct dynamics. In order to do so, we first construct local Hamiltonian. So let me define that. So let phi be an interaction and lambda be a finite subset of new dimensional lattice. Now, a local Hamiltonian on this lambda is defined by this formula. Namely, we sum up all the interaction terms inside of lambda. And out of this local Hamiltonian, we consider the Heisenberg dynamics given by this local Hamiltonian, and then take the thermodynamic limit. And if the interaction is a nice one, like uniformly bounded finite range one, then this defines this limit exists and defines the sister dynamics on our quantum spin system. The point here is that we do not have thermodynamic limit of this Hamiltonian, local Hamiltonian. However, we do have a thermodynamic limit of this dynamics. For this reason, in this framework, in this operator algebraic framework of quantum statistical mechanics, we talk about dynamics instead of Hamiltonian. And for that reason, ground state is also defined in terms of dynamics. So let me define ground state now. So tau phi ground state is a state omega on new dimensional quantum spin system satisfying this inequality. Here, this delta phi is a generator of our dynamics. So omega is a tau phi ground state if it satisfies this inequality for all A in the domain of our generator of time. So this is the definition of ground state, but it may look a bit a strange condition for ground state. But actually, if you consider this condition in a finite dimensional quantum mechanical system, you can see that actually this condition is equivalent to our usual definition of ground state. For this reason, we can regard this as just a natural generalization of our usual definition of ground state to infinite system. So that is the definition of ground state. And now, as I said in the introduction, we are interested in Hamiltonian with unique capped ground state. And so I'd like to introduce corresponding condition in our framework. First, note that there can be, in general, there can be many states satisfying this condition. Namely, there can be many ground states in general. However, the situation we are interested in this talk is a situation that there exists exactly one state satisfying this equation. Namely, the case that ground state is unique. So let me define what I mean by unique capped ground state in this framework. So we say tau phi or even phi has a unique capped ground state if there is a unique tau phi ground state omega phi and a constant gamma satisfying this inequality for all A in the domain of the generator whose expectation value with respect to this unique ground state is 0. Again, some strange inequality showed up, but again, if you consider this condition in finite dimensional quantum mechanical system, you will see that actually this is just a usual definition of unique gapped ground state with gap at least gamma. So this is again a natural generalization of usual definition of unique gapped ground state to infinite system. So we take it as a definition. Now, like this, I have introduced the corresponding condition corresponding to this first item in the introduction. And now I would like to introduce some condition corresponding to this third one, which was saying this Hamiltonian can be smoothly deformed into trivial on-site Hamiltonian without closing the gap. I would like to introduce corresponding condition in our framework. Now, so in order to do that, I would like to introduce you a classification problem of interaction with unique gap ground state. It is as follows. In this classification problem of interaction with unique gapped ground state, the object we would like to classify this one, namely a uniformly bounded finite range interaction with unique gapped ground state. And we would like to classify them with respect to the following condition, that is, two interactions in this set are equivalent, and I will write like this, if we can connect them smoothly via a path inside of this set. So that is a criterion of the classification of this unique gapped ground state. I also would like to specify what I mean by a trivial interaction here. So first, let me define on-site interaction. An on-site interaction is an interaction which satisfies this condition, namely, if X contains more than 1 point, then the corresponding interaction term is equal to 0. And as a result, the only possibly surviving terms are of this form, on-site interaction term. So this is on-site interaction, and trivial interaction is an on-site interaction with unique gapped ground state. Now you see this trivial interaction has such a simple form. All the non-zero terms are on-site, which mutually commute each other. As a result, this unique ground state is also very simple form, namely, it is of infinite tensor product form like this. It is infinite tensor product of on-site pure state. So this is trivial interaction, and now I'm ready to rephrase our third condition and third item in the introduction, namely, we are interested in interaction with unique gapped ground state which are equivalent to trivial interaction. So that corresponds to our first and third condition in the introduction. But there was yet another condition that was about symmetry. So next, let me explain about this symmetry now. In this talk, as a symmetry, I consider on-site symmetry. So let me define it here. So let G be a finite group, and let U be a unitary representation of G on CD. So here, D means this D, which was defining our quantum spin system. And our on-site symmetry is given as a group action of this G, action beta of G defined as follows. So let beta be an action of G on our quantum spin system defined by this formula, namely it is just an infinite tensor product of on-site adjoint action by U. And this action is our on-site symmetry. And we say an interaction phi is beta invariant if each interaction term are invariant under beta. So this is the on-site symmetry we consider in this talk. And recall that in finite dimensional quantum mechanical system, if Hamiltonian satisfies some symmetry, and if the Hamiltonian has unique ground state, then this unique ground state is automatically invariant under this symmetry. And exactly the same thing happens here, namely this proposition holds. So if phi is beta invariant uniformly bounded finite range interaction with a unique ground state, then this unique ground state is beta G invariant, namely this holds. Okay, now like this, I'm ready to introduce SPT phases in our framework. So now the object we would like to classify this set that is a beta invariant uniformly bounded finite range interaction with unique gapped ground state, which are equivalent to trivial interaction. So that is the object we would like to classify, and classification criterion is like this. To interaction phi 1, phi 2 in this set are beta equivalent if we can connect them smoothly via a path inside of this P beta. And as I emphasized in the introduction, now we are requiring the symmetry to be preserved along the path. And because of this additional requirement, this set may split into possibly multiple equivalence classes with respect to this classification. And the resulting equivalence class is the SPT phases. So I have formulated SPT phases in our framework, and now I tell you the main result. So recall that I said in the introduction that a physicist conjectured that for 1- and 2-dimensional quantum spin system, there are second and third group cohomology valued invariant. And the main theorem and the main result I would like to report here today is that that is the case. There is a second group homology valued invariant for 1-dimensional SPT, and there is a third group homology valued invariant for 2-dimensional SPT. So that is the thing I would like to tell you today. And for the rest of my talk, I would like to explain how to find such invariant out of our microscopic models. So the question is, how can we find such an invariant? Now, in the analysis of gapped ground state phases, there is some general guiding principle to find an invariant. That is the following. If you want to know the invariant of the bulk system, cut the system into two and look at the edge. That is the guiding principle. And this guiding principle is sometimes called bulk edge correspondence. So we decide to follow this general guiding principle as well. And following this guiding principle, we decide to restrict our group action beta to the half of the system. Namely, in 1-dimensional system, we restrict our beta to right infinite chain. And in 2-dimensional system, we restrict our beta to upper half plane. And then try to investigate the effect of this group action to our unique ground state. So that is the starting point of the analysis. But in order to carry out further investigation, there is one thing I would like to point out to you about some property of this unique gapped ground state in SPT phases. That is that they have short-range entanglement. Now, using strong tool called automorphic equivalence, which were developed in these papers, from the fact that our interaction phi in SPT phases are equivalent to trivial interaction from this condition, we can show that our ground state has short-range entanglement in the sense that this holds. So let us look at this equation. First, this omega phi 0 is a unique ground state of trivial interaction. And we know that is of infinite tensor product form. Note that this state of infinite tensor product form does not have any entanglement at all between any different sides. So the omega phi 0 is such a state. And this alpha is some automorphism which does not create long-range entanglement. For example, it satisfies the following property. So let A and B are observables localized in regions far away from each other. Then this alpha almost preserves the tensor product form of A tensor B. Namely, this holds if A and B are localized far away from each other. So alpha is some automorphism satisfying such condition, and alpha does not create long-range entanglement. So coming back to this equation is telling us that our unique gapped ground state is given as a product of this state, which does not have any entanglement at all, times some automorphism which does not create long-range entanglement. As a result, we can interpret that our ground state has short-range entanglement. That is one observation. We can one property this SPT ground state has. And I would like to have this as an input and would like to go back to our original question. So recall that following this guiding principle, we decided to restrict our group action beta G, which was defined like this, to the half of the system. Namely, in one-dimensional system, we consider this group action beta G R, where adjoint of U is applied only on the right infinite chain. And two-dimensional system, we decide to consider this beta GU, where adjoint of U is applied only on the upper half plane. And so we decide to think such a thing. And here is a question. So let phi be an interaction in SPT phase, and let omega phi be its unique ground state. And the question is, what is the effective excitation caused by this automorphism on our state omega phi? That is a question. And in order to investigate this question, I would like to recall you a list of the property we know about our ground state. First, we know that it has short-range entanglement, and we know that it is invariant under this symmetry. And with this source of investigation, now I'd like to appeal to your intuition. So let us consider one-dimensional system. Suppose that you are living in this area on the left infinite chain far away from the boundary. And the question is, I suppose that you are living in the left infinite chain far away from the boundary. And now I apply this beta GR to the system. Now question is, can you feel the effect of this beta GR? Probably answer is no, because this group action is occurring on the right infinite chain far away from you, and state has short-range entanglement. As a result, you who is living in this area, probably you don't feel much the effect of this beta GR. Next, suppose that you are living in this area on the right infinite chain far away from boundary. Now you are in the middle of this group action. But now the question is, can you distinguish this action and this action? Probably answer is no, because the difference of this action and that action are occurring in this area, left infinite chain, far away from you, and system has short-range entanglement. As a result, you who is living here, probably you cannot distinguish the action beta GR and action beta G. But now this beta G does not do anything to the system. As a result, we conclude that you who is living in this area, probably you don't feel the effect of beta GR neither. So it was pretty much hand-waving argument, but as a result of this hand-waving argument, we conclude that this effective action should be localized around this origin. That is the one hand waving argument we can carry out. And we can carry out same hand waving argument to two-dimensional system as well, and conclude that the effective excitation caused by this beta GU should be localized along this x-axis, like this. So like this, we can conclude that effective excitation for the restriction of the symmetry to the half of the system should be localized around the boundary. And so it was extremely hand-waving argument I made here, but actually it turns out that this effective excitation can be formulated mathematically, and it become our source of our index. So next, I would like to formulate this effective excitation mathematically. In order to do so, I would like to recall you some basic fact from operator algebra theory, that is GNS representation. That is, in general, for any state omega or C-star algebra, we can associate a representation of C-star algebra on essentially unique way. So here, H omega indicate Hilbert space, and pi omega indicate a representation of C-star algebra on this Hilbert space. So for any state, we can associate some representation on Hilbert space essentially uniquely, and this essentially uniquely determined representation is called GNS representation. Now, having this GNS representation, we can introduce some equivalence relation between states. That is following as follows. We say two states, omega and phi, are equivalent, and I will write like this, if their GNS representations are unitarily equivalent. So two states are equivalent if the corresponding GNS representation are unitarily equivalent. So that is mathematical definition. But this in quantum spin system, we can interpret this mathematically defined equivalence relation a bit more physical way. So in quantum spin system, we can see that actually omega and phi being equivalent means that omega and phi can be approximated by each other's local perturbation. So the difference when omega and phi are equivalent, the difference between omega and phi are just local small thing. In other words, they are macroscopically the same. So from this point of view, you can interpret this equivalence relation as macroscopic equivalence physically. And I would like to ask you to have this intuition or interpretation of this equivalence relation as macroscopic equivalence. And so it would be great if you think about macroscopic equivalence when I say two states are equivalent. Now, there is some, concerning this equivalence relation, there is some situation which become important for us. That is the following situation. So let alpha be an automorphism on a C-star algebra A, and omega a state on the C-star algebra A. And suppose the situation which become important for us is the following. Omega being equivalent to omega composed with this alpha. And this is the situation which become important for us. This is the situation we will encounter. So this is a situation, and with this situation can be rephrased with this interpretation that alpha does not change omega macroscopically. And there is one important outcome from this relation. That is, when this equivalence holds, then this alpha is implementable in the GNS representation of omega. Namely, there is some unitary on the GNS Hilbert space of omega satisfying this condition. Namely, adjoint of action by U implement alpha in our representation. So when this equivalence holds, this implementability of alpha in GNS representation of this state occurs. In other words, if alpha does not change omega macroscopically, then alpha is implementable in this GNS representation. So with this preparation, now I would like to derive second group cohomology valued index out of one-dimensional SPT. Now let us recall the setting. So let phi be an interaction in a SPT phase, and let omega phi be its unique ground state. And following this guiding principle, we decided to restrict our on-site symmetry to the right half chain. Namely, we decided to think this group action. And with this very hand-waving argument, we concluded as follows. The effective excitation caused by this beta GR on our unique ground state is localized around the origin, like this. So the effective excitation caused by beta GR is just local one. In other words, beta GR causes only local perturbation. In other words, beta GR does not change omega phi macroscopically. So that is the conclusion of super hand-waving argument, but it turns out to be true mathematically in this sense. Namely, omega phi and omega phi composed with beta GR are equivalent. So this happens, and this is a mathematical realization of our hand-waving argument. Now, from the previous slide, we know that when this happens, this beta GR is implementable by a unitary in the GNS representation of our state. Namely, there is some unitary UGR in the GNS Hilbert space of this omega phi, implementing our beta GR like this way. Now, furthermore, from the fact that our this beta GR is just a genuine group action, we can actually show that this UGR is a projective representation. Recall that projective representation is a map from group G to a unitary operator on Hilbert space satisfying this condition. Namely, it is almost like genuine unitary representation, but there is some U1 obstacle here. And it's well known that this U1 obstacle satisfies two cocycle relation, and as a result, we obtain second group cohomology valued index. Like this, we obtain some index out second group cohomology valued index out of one-dimensional system, and it turned out to be actually an invariant of our classification. So this proves the conjecture by physicists. Now, this second group cohomology valued index can be interpreted like as follows. So if omega phi is simple tensor product form of state on left infinite chain and state on right infinite chain, then this index becomes not trivial, it becomes just zero. And from this point of view, we can say that this index is showing how left and right infinite chain are correlated in terms of group action. So as we saw, our unique ground state has just a short range entanglement. So just the entanglement between left infinite chain and right infinite chain are weak. From this point of view, just looking at this weak entanglement may not be very exciting thing, but if we shed light on this weak entanglement in terms of group symmetry, then something non-trivial is occurring, and that non-trivial thing is indicated by this second group cohomology valued index. So this is about one-dimensional system. Now I go to two-dimensional system. So in two-dimensional system, we are supposed to derive third group cohomology valued invariant. So let us recall our situation again. Phi is an interaction in SPT phase, and omega phi is its unique ground state. And following this guiding principle, we decided to restrict our beta to the upper half plane. Namely, we decided to consider this group action beta GU. And with this hand-waving argument, we concluded that the effective excitation caused by this beta GU on our unique ground state is localized around this x-axis. With this hand-waving argument, we concluded so. And I try to be a little bit more optimistic and try to say that this excitation almost localized around x-axis should be decomposed into 3 parts as follows. Namely, I consider some cone with a non-zero angle like this, and I guess that this effective excitation should be able to be decomposed into excitation strictly localized in this green cone and excitation strictly localized in this blue cone and something very small, something localized around here. I guess that should be okay to imagine. And it turns out to be true mathematically. Namely, this proposition holds. So let theta be an angle between 0 and pi over 2. And let us consider this cone as I thought about in the previous slide. And this proposition says the following. For this theta fixed, so for this theta fixed, there are automorphisms localized in this green area, and there are automorphisms localized in this blue area, satisfying this relation. So let us look at this equation, what it means. On the left-hand side, that is exactly what we are interested in. We are interested in the action of beta GU on our unique ground state. And we wanted to know the effective excitation caused by beta GU on our unique ground state. And this proposition tells you that this effective excitation is given macroscopically by this automorphism strictly localized in this area and automorphism strictly localized in this area. So that is what this proposition tells you, which realizes this hand-waving argument mathematically. So this hand-waving argument is correct in this sense. So like this, we got some automorphism giving some this effective excitation caused by this beta GU. And as I said in the beginning, this is the source of our third group homology index. So let me further proceed to obtain this index. So in order to do that, I define gamma G, automorphism gamma G as follows. First, let beta G RU be a restriction of our symmetry beta to this upper right corner. And this eta GR is this excitation. So let's define a gamma G like this. And we can further show that this gamma G satisfies the following two properties. That is, one, first, gamma G itself is not implementable in the unit, implementable by a unitary in the GNS representation of omega phi. But however, this combination gamma G, gamma H, gamma GH inverse, this is implementable by a unitary in the GNS representation of omega phi. That you can show. And looking at this, this should ring the bell of some sort of people. That is, it looks pretty much similar to cocycle action. So cocycle action is some object extensively studied in operator algebra theory, and it is defined as follows. So let M be a factor, namely a von Neumann algebra with trivial center. And cocycle action on a factor is a map from map gamma from G to automorphism group on M, satisfying these two conditions. First, this gamma G is in general not inner. It is in general, it is not given by unitary in this M like this. But however, this combination gamma G, gamma H, gamma GH inverse, this is inner. This is given by some unitary like this. So looking at that, you see there are pretty much of similarity between this cocycler action and our gamma. Namely, in our setting, in our case, this gamma G is not implementable by a unitary in GNS representation in general. In their case, this gamma G is not given by unitary in general. And in our case, this gamma G, gamma H, gamma GH inverse implementable by a unitary in the GNS representation, but in their case, this combination is given by a unitary in M. So there is pretty much a similarity between this and that. And the important thing is that it is well known that out of a second cocycle action, we can associate third group homology valued index. And from this fact and from this similarity, we do expect that from our gamma G, we should be able to obtain this third group homology valued index, and that is the case. Namely, from our gamma G, we can derive third group homology valued index, and it turns out to be an invariant of our classification. And as in a one-dimensional case, this third group homology valued index gets 0 when state is just simple tensor product form. And in this case, this index shows how the system is entangled in terms of group action. So that is the end of the story, and that is most of the thing I wanted to tell you. But I would like to conclude this talk with several remarks. First, a derivation of indices for SPT phases was initially carried out in tensor network models and in these papers. And in, our indices so today coincide with theirs in those models. And as a result, there are a lot of examples thanks to these papers. Second, Taku Matsui showed that unique gapped ground states satisfy some property called split property for quantum spin chain and quantum spin fermionic chain. And using this, actually, in fact, we can associate second group cohomology valued invariant to general beta invariant unique gapped ground state. And similarly, we can derive invariant for fermionic chain. And in this fermionic chain, because of the existence of grading, the index get a bit more complex, and it takes value in this set. Third, this second group homology valued index can be used to derive Lipschutz-Matisse type theorem for finite group symmetry. So Lipschutz-Matisse theorem is no-go theorem for the existence of unique gapped ground state under some condition, including some symmetry. And traditionally, this symmetry has been some continuous one, and this continuity was used in ingenious way and to derive this no-go theorem. But using this second group homology valued index, we can derive such a no-go theorem for finite group symmetry. This is a collaboration with Yoshita Chikawa and Haruta Saki. Fourth, our approach is operator algebraic, but apparently recently there is a quantum-based, information-based approach by Kapustin and his student. Fifth, today I talked only about SPT phases. But that was short-range entanglement phases. But this operator algebraic approach can be used to analyze long-range entanglement phases, namely topological phases. For example, with Peter Narkins, we recently showed that existence of anion implies long-range entanglement. So with both for SPT phase and topological phases, there are a lot of things we can do. We should do in operator algebraic approach, I think. So thank you very much for your attention.
Thank you very much, Yoshiko, for this very nice and interesting presentation. So we'll take questions, beginning with questions here in the room. Anton, you have a question, please use the microphone.
Okay, thank you for a very nice talk. I was wondering, so you presented the one-dimensional and two-dimensional story, but how is it? What about 3D or other dimensions? Would it be a similar cycle calculation, or are there some obstructions to go to higher dimensions? Thank you.
Yes, as I said in the beginning, the expectation is this Pontryagin dual Borges group of classifying space. For 3-dimension, apparently it is still a fourth group homology. But after that, then it becomes Pontryagin dual. And for the moment, I don't know how to treat these things. And also to go to 3-dimension, there is some analytical problem we should overcome, and it's still not done.
Okay, thank you.
Next question. Please, Clément.
Thank you for the nice talk. I have a question about your original hypothesis, I think number 3. So it seems that in absence of symmetry, all phases are trivial. So maybe yes. I misunderstood. Can you comment about that?
Yeah, so yeah, I agree. It may not be very exciting just by that, but the story is that the trivial phase, which is just by that not very interesting, become interesting when you introduce symmetry. And I completely agree that topological phase is much more exotic and interesting.
Jörg, please use the microphone.
Is there a chance that you can extend this approach to one that covers low temperature or zero temperature phase diagrams in models that have different phases with spontaneous symmetry breaking possibly, rather than just one unique gapped ground state?
Yeah, that would be nice, but I don't know right now how much it's possible. Sorry.
Okay, so let's see. Sorry, I thought you were done. You are done. Okay, where is the next question? Over there, please use the microphone.
So yeah, I'm just curious if the D, so the nu is your spatial dimension and the D is the dimension of your spin space. And I guess it's not clear to me if that plays any role for what you did. Like, does this have some, like, if you fix a certain D, does that have an effect on, like, the cohomology classes that may appear or something like that? Like, does a D play any role?
I don't think so, but so for Schutz-Matisse theorem, its effect is the dimension matters, and it implies that in some D there is no unique capture ground state also. But I'm not sure right now if the result is just this one. So I don't think so.
Next question, if there is any. Please, Anton, again.
Yeah, sorry for coming back. There's one more question. So can you tailor the system to get a given cohomology class? Suppose you start not with a system, but with a cohomology class instead, and you want to manufacture a system which would realize that cohomology class. Is it possible?
I guess it's possible using this tensor network framework, but I myself didn't carry it out, so I cannot guarantee. But I guess this tensor network system, you can cook up something like that, I guess.
Any further question? I don't see any remote questions. Do you see any?
No, I see no remote questions. If you are online, you can submit questions through the live question and answer or through the discussion chat. So far, I have no question online.
So if not, I would like to take the chance and ask you a question myself. Of course, your frame is about interacting systems, but this should in principle encompass also non-interacting systems. There should be some translation to be done. And over there, there is the Altland-Zirnbauer classification or the Kitaev table, the related things. So is it correct to conjecture that there should be a connection, a sort of a dictionary, and maybe even something is known about it?
That I should study, yes. Sorry, but I cannot answer this question now. Yeah, that's certainly something I should know. Sorry about that.
Okay, thank you. Any last chance to ask questions from anywhere? I don't see any, so let's all thank Yoshiko once again.